So for today, we're going to look at some pattern analysis in our GIS, specifically using some data, focusing on Indiana workers, trying to get an idea of where our workforce is concentrated in various industries, using some census data. I can say that you'll probably be happy to know no joining of any tables is necessary for this week's activities. I'd like to start off, though, with an apology. I am both in pain and exhausted. So I had a filling pop out on Saturday. I got to tell you this, always have temporary filling material at your house. You get it for like $3 in a tube, and it's a lifesaver. You can even rebuild a tooth out of the stuff if you need to. So that's when at least I can actually sort of function. But I also ended up with like food poisoning or stomach cramping or whatever all night last night, so I'm wiped. I feel terrible. So I'm not going to be very high energy today. For that, I apologize. So for this week, the data that we're going to work with is actually on Blackboard right now. And if you've looked at the syllabus, you know that you're supposed to do 3 different cluster analyses for by next Wednesday at 5 p.m. And we're going to do one today. And we're going to do it one as best practice, but you don't necessarily need to do exactly the same thing. And I'll get to more about this in a sec. So for the class here, it helps if you pick the right class to go to on Blackboard. The data are in the week 13 folder, and they're right here. It's a almost 28 megabyte zip file. So we'll extract that. And the first one of these things that we do, these cluster analyses, you'll be able to upload as your first response of the first of 3 maps, okay? So if you want to follow along, that's going to save you a little bit of time in the future, right? You'll be 1/3 done with the assignment for this week, right off the bat. We'll leave the classroom today. At least that's the idea. And so the data are pretty, actually they're pretty involved, but let's check them out real quick before we dig into what cluster analysis is and how to do it properly. So, and we've actually done these a little bit. So the data are in the week 13 assignment 01 geodatabase. Come on. And there are 3 layers. The one that we're really going to be doing our work on is the tracts in IN plus 40, which we'll check out in a minute. So we have our three layers. Indiana outline is just an outline of the state of Indiana. So if I make that hollow, you'll see it's just outlines the border of the state, right? The next one down is tracts Indiana only. I included that for visualization purposes if you wanted to do it, but we're not going to use that today. It's up to you. You could use it creatively, cartographically, to do this assignment. And then the other one is census tracts in Indiana plus census tracts that are within 40 miles of the boundary of Indiana. Okay? And so the idea here is that if you want to find out where various types of workers might be, if you're an industry that's thinking about locating in Indiana, you might want to know what else is around, right? Especially in parts of the state that border other states. And we do have a bunch of these. So, Terre Haute, of course, is one where we border Illinois very closely. So you could maybe be pulling workers or expertise from nearby. Of course, we have our Gary, Chicago complex up here, Louisville and like New Albany, and then the Cincinnati metro area that are border areas that are really close to the state of Indiana, right? So if you were, let's say, a trucking company, you wanted transportation workers, you might be able to pull a bunch from Cincinnati, but it might be cheaper or more attractive to locate your facility there, right? That would be the thinking. Okay, so we have these data, and what's important to know, well, the first step in exploring patterns might be something like, well, let's make an overview map of, let's say, the number of workers in a certain industry, right? So we might go to, not categories, but quantities in the symbology tab of the layer properties dialog box, and switch the field that we're interested in to, I've got to scroll way down. Here it is, employment 16 and up in, I don't know, what's an area that's interesting for employment? Jaleel, when you're done, where do you want to work when you graduate? In what sector of the economy? Mining? Okay. David, when you graduate, where do you want to work? What sector of the economy?
The civilian sector.
Civilian sector? Okay. Doing what?
Hopefully geospatial stuff.
Okay. So maybe we could go to professional tech, right? So this is, in 2014, the number of people employed who are 16 years of age or older. Why 16? Because you need special permission to work before you're 16 if you're not working agriculture, right? In the professional or technical industry, right? It's going to include geospatial stuff that's non-civilian, or that, and it's going to contain other stuff, professional workers. But all things considered, you tend to find these types of jobs clustered together. And what do you notice? If we just go with the defaults, we do notice some, visually speaking anyway, some clusters, right? Where do you find professional and tech jobs in Indiana and the surrounding counties?
Major cities.
Yeah, you find them in the major cities. Indy is one, a little bit around Fort Wayne, some around Gary, maybe some around Cincy, a little bit in the southeast, right? There's actually a large geospatial consulting firm down in Evansville, so that might actually be loading into these numbers, right? But what's the problem with this? Would you use this to decide where you're going to move and then apply for jobs there? Probably not, right? But if I told you this would be a bad way to make decisions, what would I be saying? Why would I be saying that? Well, the Evansville anecdote I just gave you is a good example. Maybe there's one employer that's overburdening all the other data in a census tract, right? So an example of this might be like, let's say that this is a map of pharmaceutical industry, right? And all of a sudden, in this census tract here, it was way above everybody else. Why? Well, because Eli Lilly's corporate headquarters is right there, right? Does that mean that that's a better place than all the other tracts for you to get a job in that sector? Maybe, but not necessarily for sure, right? It might be that they are only hiring research-grade scientists, not, entry-level lab tech or whatever the job description might be that you're qualified for. So this isn't a systematic display. I mean, it is in the sense that it is the number of employees in the tech and what is it? Proportion or professional and technical fields, right? But it's not telling you whether these tracks stick out actually, statistically speaking. There's no, it could just be an outlier. And so to study clustering appropriately, we would want to take these data and actually run a statistical test. And in this case, the one that we want to run we've actually done before in this class. It's called GIS Ord. And it's called Hotspot Analysis. So if we open up this tool, and if you open up this tool, no, this is a bad sign. Come on. It'll crash ArcMap. It's called Hotspot Analysis. Or if you search, I search for GEDIS because I happen to know that's what it's called. GEDIS Ord. GI star. Bless you. I'm going to close this out and try again. Did anybody else have this problem, or did it start up? Yeah.
Is it hotspot analysis with rendering?
They're the same.
Oh, okay.
Hotspot analysis with rendering is like a legacy tool, so they don't use it anymore, and hotspot analysis does the exact same thing. They just changed how they run the tool in the background. So it still exists there and works in case you have like a script or a program that you wrote that takes advantage of that tool. They just have it basically for legacy purposes, just in case there's something you have that needs that particular tool to run. Okay. So let's see if I can get it to work again. Yeah. Okay, so as any tool, you have to have inputs and outputs. And in our case, the input's going to be our Indiana tracts, right? So these are just census tracts in Indiana and the surrounding 40-mile radius, right? And our input field is going to be, oh no, how do we know which input field this is? Well, there are two ways that we can figure out what the actual field name is. The first one would be to open the attribute table for our census tracts, and then to scroll over and find our column of interest, because it's displaying here not the actual column name, but an alias. Column names can only be 8 characters long or something like that, maybe 10 in a geodatabase. Aliases can be very long. So the name of this column is MAGE25_CY, but the alias is 2014 male population age 25. So we just need to scroll over till we find our industries. Where are they? So that would be one option, but it's not going to be very quick to do that. So the other option would be to go to the data that I downloaded and see if there are any metadata. And while there aren't any metadata in the ARC catalog sense, there are some metadata in the zip file, right? This 2014 Esri demographics complete. And if we open this in Excel, there's a variable list. And this variable list might be easier to find the column name that we want. So I'm scrolling down till I find our employment data. Oops, I think I just went by it. No. Net worth, home value. Maybe I did. Yeah, I could do that. Prof Tech. Here we go. So I wanted employed though, not industry. So occupation. That's not what we wanted though. We wanted
deployed. Well, here we go. Tech CY. Let's make sure. Yeah, Tech CY is the name of our column. There it is. And then I have to select a place to output the analysis of the hotspot tool, right? So I'm going to do that. Call it Hotspot Tech Prof. But then I have two things to deal with. The first one, and this is something I glossed over the last couple of times we've used this tool, or last time we used this tool, and those are, we have to come up with a conceptualization of spatial relationships, and we also have to come up with some kind of distance method. Because a hotspot is only a hotspot when compared with its neighbors, right? So like think of a high crime area. Like, I don't know, maybe there's a high crime area that you're aware of. Is it a high crime area compared to all places on Earth, or just compared to the city that you're talking about, right? So in Indianapolis, the east side of the city is a crime hotspot, right? But if you compare it to all cities in the world with a population of, say above 800,000, it is not a crime hotspot, right? Indianapolis doesn't come out in a top list anyway, right? So we have to think of how we're going to conceptualize these spatial relationships and then how we're going to actually measure them. So the first one, the conceptualization part, is something that you've got to think about carefully. And so let's read up on the methods that are available to us. The first one is inverse distance. And basically this is good for, it says nearby neighboring features have a larger influence on the computations for a target feature than features that are far away, right? Well, farther features not being in it so much is a good thing if your concept of spatial relationships is completely dominated by spatial autocorrelation, right? The idea that close things are more related to others. But inverse distance is going to really emphasize places that do stick out. So if you're more interested in finding overall trends or like zones with, say, high professional tech and scientific employment, rather than little islands, you might not choose this, right? The next one down is inverse distance squared. But here, this is definitely going to emphasize, because it's got the square in it, it's going to definitely emphasize the island nature of hotspots and ignore maybe some close features that aren't so hot, but are still hotter than you would expect, right? The next one would be fixed distance band. So this is basically saying, hey, if anything is within so many feet or so many miles of my current location, then it forms part of a potential cluster, right? Zone of indifference is a weird one. It sounds strange, right? But basically, here there's a critical distance, and then outside of that critical distance, weights diminish. So essentially, you're saying, hey, emphasize neighbors, but as we get further away, there should be some role that they can play in determining a hotspot. Does that make sense? Sort of like a buffer, right? Like if you're in the donut hole, there's the radius of the donut around you that you would consider neighboring, and therefore more likely to form some kind of cluster. But then as you get away from the donut, you're still likely, but less and less likely to be part of any potential cluster. There's contiguity edges only. So this is nice if you've got polygon data like us, and so you'd say only those those areas that touch the current polygon might be considered. We might say contiguity edges the corners, so any place where there's an overlap or a node shared will be potentially in a cluster. And then we could actually define these spatial weights or these spatial relationships manually. Now I can say ideally we'd like to define these manually, but creating a manual definition of whether a place could form part of a cluster or not is a huge undertaking. Because, let's see, how many census tracts do we have in this data set? Let me find it out real quick. Come on. We have 4,169 census tracts in this data set. If you wanted to manually define whether they'd be, say, neighbors or not, you would have to have a 4,169 column by 4,169 row matrix of weights, where, census tract 1 was not a neighbor with census tract 1, but is with 2 and 3, but not 4, 5, 6, 7, 8, 9, 1,000, 4,169. Get what I'm saying? It's like a cross-tabulation of every single potential match that could exist. So it's a big spreadsheet that you have to manually make. So most people don't specify manual weights, right? Specify weights on their own. For something like, is there a cluster of tech jobs, right? Which of these spatial relationships seem to be of interest? Or which one would be likely, useful, usable? Yeah, inverse distance, probably not inverse distance squared, right? It's going to drop off too much. So inverse distance could be good. We might do you might do direct contiguity, so edges only maybe, or you might do zone of indifference. Right, those are three that I could think might be useful in this context. Are there clusters of tech jobs in, Indiana and its surrounding counties? Okay, so maybe we would choose something like zone of indifference, right? Remember, zone of indifference would be like immediate neighbors have a very high likelihood, and then it drops off after there, right? So basically, if like our census tract here that ISU's at has a high number of professional and tech jobs, the tracts n feet away, right, or n meters away, or whatever it is, n rods distance from here, are going to have a high, are going to be highly likely to be part of a cluster, and then that likelihood will drop off with distance away. So let's choose that for this case. Zone of indifference. Well, the problem is that zone of indifference does require some notion, most of these do, some notion of where the critical distance might be, right? So is it just 1 foot away from the centroid of the census tract? Well, no, that's going to be in the census tract, right? Is it 1 mile away? Well, that might be too far. Or that might be okay, but 20 miles might be too far, right? Incidentally, what's the difference between Euclidean distance and Manhattan distance? Anybody know? Yeah. So Euclidean distance is straight from one point to another, like as the crow flies, right? What's Manhattan distance? You could define it like they say here, right? So the distance between 2 points measured along axes at right angles. Or it's really part of the taxi driver in Manhattan situation, where you've got, boulevards and avenues or whatever, and, here's your origin, here's your destination. It doesn't matter, because the taxi driver is constrained by the gridded street network. It doesn't matter if they go here, right, here, or something else. They're going the same distance, right? So you could have a concept of distance, Manhattan distance, but that doesn't really work very well in our types of applications, at least in this application. So anyway, we need a distance threshold, basically a place because we're using this zone of indifference, we need to define what that zone is, right? That zone where it's got to be a neighbor. And so how would you come up with this number? It's a numerical distance. How would you come up with a number that would correspond? Would you just pick a number? That's what we've done in this class so far. And that's what a lot of people do. They say, well, something's a neighborhood as long as it's within, half a mile of this location, right? That's sort of within my neighborhood, right? Which is sort of what we're saying here. Tech jobs cluster together when they're found immediately in the same census tract or in immediate census tracts, right? That would just be a contiguity definition. But we want to get fancier than that. We've got to figure out where that distance might happen. And so, excuse me, we could just pick a number based on our expert knowledge, but how many of you qualify yourselves as experts in the clustering of science, tech, and professional jobs in the state of Indiana and surrounding counties? Right? I wouldn't, despite the fact that I have one of those jobs, right? I definitely wouldn't say, well, we could test that I am an expert in that. But we can actually come up with a distance value in a replicable fashion, right? One that's not subjective or just a guess. And to do that, we can actually use the Spatial Autocorrelation tool, Global Moran's Eye. So have we used this tool? We used this tool in this class, right? Moran's Eye? Yeah, a couple weeks ago. And what the Moran's Eye tool does is it just tells you whether spatial autocorrelation exists in your data set, right? That's all it does. And we actually have input fields that are exactly the same. So in this case, we want it to be IND tech.cy for our tracks in Indiana and 40 miles. We want our conceptualization of spatial relationships to be zone of indifference. And then we still have to specify a distance band. But what we want to do here is test a bunch of different distances. We don't want our distances to be too small because then you have no neighbors, right? We don't want them to be too big because then we might as well not be running and clustering this based on distance at all, right? So we've got to come up with a number. And what Moran's Eye does is it gives you a measure of how extreme the spatial autocorrelation is in the form of something called a z-score. When a z-score is 0, right, basically you're looking at what would be expected to be an average value of spatial clustering. Or basically no spatial clustering in the case of Moran's Eye. There's no spatial clustering. If you have a high positive z-score, something above 2.5, right? That means there's positive spatial autocorrelation, that high values are clumped together. And if you have the Moran's Eye output z-score is a negative value below 2 or negative 2, negative 2.5, you have negative spatial autocorrelation. Basically that high values and low values are found near each other, which is weird. Right? You never expect to see that, almost never expect to see that in the natural environment, or even due to random chance. Right? And to put it into context, basically Moran's Eye is whether there's spatial clustering or whether things are random. And if you get a Moran's Eye at or close to 0, chances are your data are randomly distributed in space. Right? So what we want to do here is actually try to figure out when those z-scores start to change. So we might say, look at these census tracts and say, all right, well, let's go 500-meter chunks, right? So we might say, we'll run a Moran's Eye first at 500 as our distance band. And it's going to run. It doesn't take too terribly long to run. And I want to look at the results of the Moran's Eye calculation in my results window. It's still running. And I might want to make a little table, so I'm going to have our Excel open here in the background. So I have distance, and I'll have my z-score as my columns. Still running. Oh, there's a warning. What does the warning say? It says, the number of neighbors for at least one feature exceeds 500 meters. You might want to change your conceptualization of spatial relationships to avoid the potential of running out of memory, or exceeds value. So that's when a place has more than 1,000 neighbors. So that's why it's taking a long time to run. I might cancel it. Maybe we'll go smaller. Instead of 500, maybe we do 50. Number of neighbors for one feature. Hold on, let's see. So can you think of some reasons why 50, a number of 50 would yield way too many neighbors? Like if we zoom in on the census tract that we're currently in, or nearby anyway, and we measure using the measure tool here, like how far the center of this is to the edge of the next one. It's like 847 meters, right? So why am I getting too many neighbors? Can you think of any reasons? One thing to always check with when you're doing distance calculations is to see what your projection and coordinate system are. Hint, hint. So what's the problem with web, auxiliary, sphere, Mercator projection? What's the problem with it? What is it good for? What doesn't it do at all?
Is it because it's a sphere?
Yeah.
You're doing straight lines.
Yeah. And so how do you measure distance on a sphere? Technically. Be in like radians or degrees, right? Not in degrees, minutes, and seconds. Not in meters. So we have a situation where we need to project our data first to do these calculations. So we do a project. We want to project our data. So we would go here to tracks Indiana. I'm going to save it to my same geodatabase, but call it but have a projected on the end. And then we have to pick a coordinate system. What? Do we want a geographic coordinate system or a projected one? We want a projected one. Geographic is going to be in degrees and degrees of latitude and longitude. And so now, kind of to walk you through this, the thinking on this, what would be the next thing we want to do? Well, we want to look at probably not a state system because we have stuff outside of the state, right? Stuff in Ohio on both sides of the state. But we might want to go with a UTM projection, right? UTM's good at area and distance within its zone. And in this case, what would we want to pick? We're picking our datum next, right? Do we want to pick a North American datum or a World Geodetic Survey datum? This is a tough one because initially you'd maybe expect to pick a North American one because Indiana's in North America, right? But our original data are in WGS. How do you know? How do I know that? Magic. No, because it said so in the layer properties dialog box, right? The source tab. So we want to match that so we're not adding distortion or having to do a geographic datum transformation. But we're in the northern hemisphere. And then how do we find out what zone Indiana's in? How would you do that? Google, right? UTM zone map. And here's a nice one in North America. It looks like most of our data are going to fall, if not all of them, into zone 16. That's one of the benefits of being in Indiana, right? It's all in one zone. You can see most states in the country are not in that situation. In fact, it looks like Indiana, South Carolina, West Virginia, Alabama, and that's it, are in one zone. Maybe Rhode Island. And New Jersey and Delaware, sorry, are in one zone. So there's some. So we picked 16. And hit OK. And as that runs, I'll open up my spatial autocorrelation box here. So what we were saying when we said 50 or 500 was 50 degrees of distance. Where would that put our line? Like say 50 degrees out from Terre Haute on the globe, east. Where would our line be approximately? Anyone know our degree, our longitude, our degrees longitude here at Terre Haute? So if we pull down this globe, which is hopelessly out of date, it's pretty hard to read degrees because it's all screwed up. Right? And we are like negative 87 or something like that. And so 50 would put us over by, I don't know, maybe Bermuda. So of course almost all of our census tracts were neighbors with each other. Right? We had a 50, well, it was 500, we definitely did. We had a 50 square degree box that everything was fitting inside. So when we say 500 now, it's going to be in meters, right? So I want to add my projected data in here. Everything else is going to stay the same. We run this. Notice we have no errors now so far. Oh. Still saying 1,000. See how long it takes to run. Too long for my tastes. All right. So let's see. Why don't we try a different concept of different distance so we can actually go through this. We'll go with inverse distance, which we were suggesting earlier, right? See if this will run more reasonably. Normally, you'd want to go with what your concept actually was, but we only have half an hour here, so I want to see if we can get through 10 of these runs. Didn't run. What happened? So now distance band is too small. 500 meters means that some of these places don't have a neighbor. So let's go up to maybe we'll start at 10,000, which would be 10 kilometers, right? Taking a while. So now I have my values. I have a z-score of 239.21. That's huge. Essentially meaning that I almost certainly have clustering in this variable. And it is not due to random chance. So I put my z-score in here, 239.21. 239.21. In other words, this is telling me across all of my counties I definitely have clustering. But now I want to say, well, what if I mess with my distance, right? Because that's what we're trying to figure out. What's the appropriate distance to use in my cluster analysis? So maybe I add 1,000 to this, right? So it goes from 10,000 to 11,000. Remember, outside of the higher your z-score is positive, the more positive spatial autocorrelation you have. The higher it is negative, the more negative spatial autocorrelation you have. And in this case, after my second run with 11,000 distance, my z-score goes down to 238.79, right? 238.79. Then I run it again. I'm going to run this 10 times, right? With incrementing my distance by 1,000 meters every time to figure out where the appropriate distance band could be eventually. So I'll run this again. So do you want to see a trick? Check this out. So I can find my spatial autocorrelation tool. While this is running in the background, I can right click on it and go to batch. This can be really useful. Essentially, it's a form that I can fill out to add, let's say, 8 runs of the same tool. Right? In this case, I'd probably want 7 runs of the same tool. My third run, my z-score is 238.41. 238.41. So without knowing anything about programming, if I don't want to know anything about programming, I can still do, let's do this. I can still do IND, what was it? IND tech. Inputs. IND tech underscore. So check this out. IND tech underscore CY. I can have my distance band be 13,000. And then I filled it out once. I can just say, all right, make me another one, make me another one. So there's 7. It'll get me to my 10. And I just have to go in and change this to 14, change this to 15,000, 16,000, 17,000. Right? So everything else is the same. I'm just changing the distance. And I hit OK, and it's going to run this tool 7 times in succession. Or crash. So you should be aware of batch processing, right? That's what that's called, is batch processing. So it's going to start off with the first one. And what we're trying to do is generate values, these z-scores, these indications of how extreme our clustering gets, right? And we're going to make a chart. And that chart is going to show us where the extreme values tend to fall, or at least where z-score values change. And that's what we're interested in, is an inflection point on a graph that tells us the distance that we're interested in, or distance that we would want. So this is 13,000, gives us a z-score of 238.69. This one here is, right here is, well, let's see where it puts them. 1447. So sticks them on the end. So 13,000, this is 14,000, has a z-score of 239.33. $15,000 has a z-score of 239.72. $239.72. $16,000 has a z-score of 239.84. Let's see where I'm finding that right here. $17,000 has a z-score of 239.42. You can run batch processes for almost any tool in ArcMap. Save you a lot of time. Set it and forget it, kind of. So anyway, we would go on. Here's my 18,000, has a z-score of 238.73. Well, I guess we'll wait for the last one. Now, why would I stop at 19,000 meters? Or why wouldn't I? Well, your test of this, what the optimal distance is, your threshold distance, should be determined by the spatial phenomena you're looking at. So what I might want to do is actually think, well, how far would somebody be willing to commute? Or what are some other factors that might influence the presence of tech jobs, right? Maybe it's proximity to fiber optic internet connection. Maybe it's proximity to a major highway. Maybe it's proximity to an airport. Maybe it's proximity to state government. Maybe it's, there are all kinds of things that might influence it, right? And so then I have to think, well, what's the maximum distance that I would be willing to travel? Or what's the maximum distance I could run a new fiber line? Or what's the maximum distance that I would accept being away from the state capital for my tech job, or whatever it might be, right? And that maximum distance that you come up with conceptually is going to constrain the upper limit. And your bottom limit is going to be the minimum distance that would separate one cluster from some other factor that would make a jobs cluster there, right? So you might be running a Moran's eye in this fashion hundreds of times to legitimately derive correct threshold distance, or at least an empirically supportable threshold distance. What we're doing here is just constrained by our time limits, and also the limits of your sanity, right? I'm not going to ask you to do it a bazillion times for every one of these variables. So in this case, for 19,000 meters, the z-score is 237.93. So then I would just take these data and I would graph them. I want to make a line graph. And what I want to do is have distance on the x-axis and z-score on the y-axis. So I'm going to change my, remove this as a whatchamacallit, as a series. And then I'm going to make sure that my horizontal category labels are my distance numbers. So what do we see? What do we see in the z-score trends? Where is our first dip? Well, our first dip is actually at the very first data point, which to me indicates that probably 10,000 meters is too big of an initial distance to start testing. But we're not going to go back and add more because we only have 20 minutes, right? So, but what you might want to do is if you did get a situation like this, you go back, right? Run some more at the bottom end. And so then we see it go down, and we see it come up again, and then the next point at which it goes down, the z-scores go down, is about 16,000 meters. So what that means is that our spatial autocorrelation values start getting less intense at 16,000 meters, meaning that would be one critical distance. Probably the other one was at 8,000 or 7,000 meters, right? So you use this as a diagnostic. Come up with a threshold where your spatial autocorrelation is highest and starting to drop. Does that make sense? Remember, what we're trying to do is group values, come up with statistically significant groups for tech jobs, right? And we're specifying where the threshold is where we don't consider it a grouping, essentially, or where we think groups would end. And what that means is we think high values would start to decline as we start to get away from that distance. Right? So anyway, in this case, we'd probably find a lower number if we ran Moran's eye a bunch more times. But in this case, we'll go with 16,000 because that shows a good inflection point on that line. So 16,000 meters would be an appropriate distance band or threshold for our hotspot analysis for only these tech jobs. We would have to rerun this for the other ones, right? For any other variable that you would pick in employment. There are some tools to help you do this more rationally, including this incremental spatial autocorrelation tool, which will run Moran's eye for a whole bunch of them, right? So same kind of deal here. We could go tracks Indiana. We could find our IND, is it IND tech? Yeah, underscore CY. We could have it run 10 distance bands, the beginning distance being 5,000 maybe, and the ending distance being, and the increment being 1,000. And it's going to output a table for me, which I could open in Excel or wherever. Incremental spatial autocorrelation. And it will do all of this so I don't have to make a whole bunch of tools or a whole bunch of spatial autocorrelation tool runs. But it's going to run Moran's eye 10 times. It's going to take a little while, right? In this case, it failed. I'm not going to take the time to figure out why. It says none of the features have neighbors at the following distances, which we know not to be true, so I don't know. Maybe my inputs are wrong. Anyway, so there are tools to help you get this done more rationally. But in our case, maybe we want to set our distance band to 16,000. Not 160,000, 16,000. And why 16,000? Because it's where spatial autocorrelation declines in the graph that we made that somehow is changed. Right? It's where the data, the inflection point in that line corresponding to distance and z-score occurs. Still running our analysis. So while this runs, what problems are folks running into, if any, with the assignment that's due Wednesday?
I don't know yet.
I was going to say, start with you. So some tips. One, you need to make sure that when you do the table join, that your data types agree. So just because it looks like it says 10106, right, doesn't mean that the computer believes that they're both 10106 when you do the join. They both have to be the same data type, string or long, right? You'll want to beat your head against the wall if you have one in string and the other in long, or vice versa. So make sure your data types agree and your join will work. Just because it looks like the numbers are numbers in Excel when you open up the CSV file doesn't mean that they are. So you might have to do your number conversion, your text to number conversion from your county's data set in order to make the join happy, right? Happen happily. What else? ArcGIS 10.1 sucks at joins. So be prepared. Anything else about it? No? Okay. So I'm concerned that I didn't do a very good job explaining why we were making all those Moran's I calculations. So to get at z-scores, z-scores are put values on a number line, right? And the values are standardized according to the mean and standard deviation of all your data values. So if, let's say you had number of tech workers, right? And let's say that the whole number of tech workers in the state of Indiana was 10,000, right? And the standard deviation was 300. Which would be great if the standard deviation was low, right? But it's relatively low. But let's say that those are the numbers, that your standard deviation was 300 and your mean was your x bar, should be mu in this case, is 10,000. So you can do with a quick equation, basically some ratioing. You change these values, your observation value, into a standard number that fits along a number line where most of your values are going to be at 0, right? 0 is going to correspond to your mean, essentially 10,000 in the example I have up here. And then if your standard deviation is a nice low, in this context 300, it might be something like this, right? Where that means most of your values are either up 10,300 or 9,700, right? But basically, most of your values are in this area here, underneath this curve. It should be bumped over, but most of your values are right in the middle here. When you have a value, though, an extreme value, right? Like say a county here that has a ton of tech workers, their number is going to be maybe out here on the z-score chart, right? Which means it is an extreme outlier. That's what z-scores are. They standardize our data set so it's got known characteristics. So when we do z-scores for tech workers, the Moran's eye calculation, that z-score tells us how extreme they are at various distance bands, how extreme that correlation is. And when it starts to decline, when it reaches a peak, that's maybe an important distance for that phenomenon, 16 kilometers. So we have a cannot create output problem here, which is disappointing. Okay. Try saving it at a different location. So as we generated those z-scores for various distance bands, what we're really doing is just trying to figure out where we have optimal, at what distance we actually do have autocorrelation occurring, or more extreme autocorrelation occurring, which would be indicative of a cluster. Fail? No, it didn't fail. It's running now. Any other issues coming to mind? Cropping up? No? Okay. Good. So why do you think it's taking as long as it is? It's the same answer every time I ask that question. There are 4,167 observations, right? A lot of observations to churn through. It's got to take every one of those observations, figure out what's 16,000 meters away from it, and then do a calculation to come up with a cluster z-score and p-value. The z-score, as I kind of told you, tells you how much of an outlier the place would be, and so we would find the output from this test. If it's got a high z-score, it's an outlier. Or a very low z-score, it's an outlier. So clusters of low number of tech professional jobs or high numbers of technical professional jobs. And then the p-value will tell you whether that clustering is how likely it is that clustering occurred due to a random chance, which is a factor when we look at clustering. Is Terre Haute a good place for plastics because we do have a lot of plastic film manufacturers? Is it because there's a good reason, or is it just because randomly Terre Haute managed to be an attractive place at the time of plastic film manufacturer site selection processes? I don't know. So you typically have to look at two values when you do this kind of work. One will be the z-score to tell you how outside the norm in this data set the observation is, and then also the p-value. Because you can have high z-scores, but a very high p-value as well. You want p-values to be low. And if you had that, it would be an outlier, but let's say 90% likely that that outlier is an outlier due to random chance. Well, that's not going to be something that I'm going to want to say is a cluster, right? But if it's 5% likely that that cluster exists due to random chance, then you're more likely to accept it as a cluster. So it succeeded, and it's going to color the state of Indiana according to the hotspots and surrounding areas, the hotspots that exist, which is fortuitous because I've got a boogie right away after I describe this, unfortunately, for a committee meeting. But if we were to look at just Metro Indy, we have some places that have, let's say, high and low clustering, or actually, it's all high clustering, high p-value, or high z-scores. So if I click on this one tract up here, and I scroll down to the very bottom of my data set, Hotspot Tech, click here. I have a GIS score value of 2.8, which means it's fairly, it's fairly high there, and a p-value of 0.005, essentially a 5% chance that this cluster here is due to random chance, right? Same thing if I look here, the z-score is actually a 5, so even stronger cluster, and it's less than 1% likely that that's clusters due to chance. Let's see if I can come up with a low cluster. Hold on. Doesn't look like there are any low clusters in the data set, which is interesting. Right, there are just either no clusters or some high clusters. So the assignment for this week is you're going to run this GEDIS G hotspot analysis for 3 employment variables for this data set. Okay, so 3 sectors of the employment, and show where Terre Haute might exceed its neighbors or the rest of the state, or like in this case, be no better than its neighbors. So Terre Haute's not the place you want to try to get a tech job, maybe. There's not any high-tech or professional clusters, although you'll find that some professional jobs, like in the health services fields, et cetera, are broken out into different categories and would be clustered in Terre Haute, perhaps. So you're going to run 3 of these. Now, I'm not expecting you to do the Moran's eye charting thing, okay? Because that'll be pretty time-consuming, processing-intensive. But you do have to think about your concept of distance for the employment variable of interest, because it's going to be different for different employment areas, and how you came up with a critical distance threshold for each of those variables. So again, you got to think about, what is it that's important about this particular industry, for its workers, because this is employment that you're talking about. And then you got to provide those rationales and upload the maps as a PDF to Blackboard by next Wednesday night. Any of the jobs that are in the data set. Yeah, any of the employment areas that are in the data set.